Earth science time. Today we are talking about Earth. Oh yes, please let the record show. This is if for those of you taking notes on my garment, which I assume is the main reason anyone would ever come to this class. Certainly watch the videos is to see what the fit is. You'll astute observers of the channel and therefore the fit will see that this is the same outfit I was wearing in my previous video. But guess what? It's the same day. You can also tell from the sign, December 8th. Today is December 8th. What day of the week is it? Monday. Today is Monday, December 8th. And today's topic for Earth Science Time is Earth. But that's not all. It's earthquakes. One day my son asked me, what is an earthquake? That's a good question for a 3-year-old. You guys are older than 3-year-olds, but it's a good question for you too. What is an earthquake? If a 3-year-old asked you, what is an earthquake, how would you describe that to that person?
Land shakes and cracks.
Okay, I kind of like that because we're just starting with a synonym for earth, which is the land, and a synonym for quake, which is shake. And that it sounds like I'm making a joke because of the tone of my voice, and I kind of am, but really that's a pretty good start, at least. We could say at least a symptom of an earthquake is that the land is shaking. Does it have to just be the land, by the way? I mean, yeah, you could say that when we talk about land in like our, I don't know how daily this comes up for you, but in the daily sense, in the layman's sense, we usually mean dry land. If we substitute this word for crust, I think that would get us a little bit more precise. Then shake, does there have to be movement? And in fact, if the answer to that is yes, which first of all, yes or no, does there have to be movement?
No.
It's a scary question, isn't it? Because I'm making it be a yes or no question. It's a scary question because it seems like anytime does there have to be is the start of a sentence or the start of a question that the answer must be no. Because could you think of an circumstance where something doesn't shake? Probably, but in general, kind of by definition, it does need to have some movement. So let's put that here. And not just any movement, but specifically we're talking about oscillation. Have you heard the word oscillation before?
No, a few times.
Okay, what does it mean?
Oscillation usually means back and forth.
Yep, exactly right. I was going to use those exact words. Oscillation means back and forth. In science, specifically in physics, we call this harmonic motion. More specifically, we usually call it simple harmonic motion. The classic example of simple harmonic motion, find a classic example of this in my desk drawer. You can find classic examples of many things in my desk drawer. That's why I have a desk drawer, is to bring out classic examples of things. This will work. I can make it better with this, though. Here I have some classic examples of science objects. String and ball. I think I'll just use the string this second. The classic example of simple harmonic motion is, this is going to be super, probably impossible to see on, I'll do it in front of my shirt. What's this? Yep, it is moving. You know the name of this thing? Pendulum. Yeah, it's a pendulum. The classic example of simple harmonic motion is a pendulum. Back and forth, right? Whoop, bonk. Back and forth. And this is an oscillation. This is an example. And we can see, if we have this going through time or space, you can see what starts out as back and forth is, as it goes through time and space, is this. And what did we just diagram here? Like if I were doing what I'm doing is this, you see. And so if we trace that, we get this exactly right, a wave. And that's the main thing we're going to talk about today in earthquakes, which, give me the fancier name for earthquakes.
Crust oscillation.
Okay, that's good. I like that. You just made that up, but you just taken these two things that are fancier versions of that. So we could say, if you're trying to tell a 3-year-old, what's an earthquake, Daddy? The 3-year-old says, a land shake. You could say that to a 3-year-old. If you're trying to convince your science teacher that you know what you're talking about, you want to sound professional, you could say crust oscillation. You're not wrong. But even fancier, a Latin or maybe Greek word is
Seismic wave.
Seismic wave. Seismic. I was going to put seismic activity. I like seismic wave too. Seismic wave. And that's the mathematical representation of an earthquake is a seismic wave. what are the components of this wave? Well, I don't mean in general waves. If you are having a hard time remembering the general components of waves in general, you can either look back in your 8th grade or 9th grade science notebook, or watch videos where I've done that for both of those classes, 8th grade science and physical science, on what a wave is. But for an earthquake wave, we really have, of these waves, there are 3 different kinds. What are they?
Primary, secondary. Oh, let's see. I had it. Never mind, I don't have it.
All right. You do know, though. Surface.
Oh, I knew that.
Yep. And let's talk about the differences among these. Let's do orange for differences.
Oh, surface is the one that has to be on surface.
Yeah, that's right. But let's rewind, both of us rewind 2 steps. What is blue? If orange is representing differences, what's the blue representing? We do differences over here in orange. Yeah, similarities. They're all back and forth, simple harmonic motion waves. They're all crustal oscillations. So let's talk about P waves first. P wave, which is short for, as you say, primary wave. Why called that? What does the word primary mean?
Very first.
Yeah, first wave. The first wave that emanates out from the structure of an earthquake. This is a little by the way. If we have, where is earthquake happening, do you think? What have I just diagrammed here? Very simply. In the lightning bolt. What do we call the lightning bolt in this diagram? Can you guess? Usually a fault. Usually either it will generate a fault or it will happen at an existing fault. And the place where the earthquake is happening is called this is a vocab word. It does not start with an E. Don't say the E one yet because you're going to be wrong. The actual location, 3-dimensionally, the focus. There we go. But the place on the land directly above the focus is called and this is what you were going to say, maybe, I hope not. Epicenter.
Oh,
What's the prefix epi mean? As in epidermis or epinephrine or epipin, which is short for epinephrine pin. What's epi mean?
Epic.
No, not quite. It could be. It doesn't know. Epi, the epidermis is what dermis? The whattermost part of the skin. Outermost, right? Something that is, I'm trying to think of examples that aren't that hard. I was going to say epigenetic are traits that happen outside of the actual coding of the genes, but epi generally means on top of or on the outside of. So the epicenter is outside of the center of the earthquake, which is the focus. And so the epicenter is the place on the surface that correlates. But you see how, since we live on the surface, here's your house. I assume you have a chimney so Santa can get in. Well, look at where the epicenter is compared to where the fault is. We can find this fault in real life. A lot of times it does come up on the surface. But you see how it sometimes can be miles and miles and miles or kilometers if we're using science away because the focus is down here and the fault might not be directly a straight line. So anyway, the primary wave is the first one to come out from the focus. The first one. That's all primary means. A lot of times we use in our daily life primary to mean the best or the most important thing, but primary really just means the first. And it's called the first because this is all from the standpoint of a seismologist, someone running a seismogram, which is a machine that measures earthquake waves. They first record the primary waves. Why? Why would I, if my house has a seismogram in it, why would I record the primary waves first? Because they are the first ones to get there because they move the fastest. And how do they move?
Oscillating.
Yes, not false.
So it's upwards and downwards.
Is that right though? I'm trying to find it because you can see how I might get confused about this, and and that kind of tacitly gives you permission to get confused about this. Have to review myself. Please forgive me. Okay, yeah. The primary waves, unfortunately, Will, I'm so sad to have to remind you or to tell you that you were Incorrect, but that's okay. These ones are transverse waves. Which means if the energy is flowing out from the focus, which it is, the particle motion is in the same axis as the energy motion. Energy in same axis as particle motion. Does that should be reviewed? Do you remember the example we used for transverse waves in 8th grade science or 9th grade science? It was a toy. I'll give you that hint. What was it? What toy? What toy did we use to demonstrate transverse waves in 8th and 9th grade science when we talked about these? I think you guys are not in the same class, but I have done this 12 times, so probably you were there for some of it. I was standing here, someone was standing right off the side, and we both held one end of something, and I pulled it, and it went back and forth like this. Do you remember what nope, it wasn't a string, because you can't really do that with a string. You pulled it, and it compressed, and then it went...
Oh, the little lungy thing.
Yeah, but it wasn't that. It was a... No. Oh, no.
The thing that all the moms have.
No. And I'm not a mom, and I have those, and I used them 20 minutes ago. But what I'm talking about is a slinky. So we had this. This is a very poor drawing of a slinky. But we had this slinky, and I would squeeze together, making a compression here, and that compression would move throughout. Now, was each individual coil moving from me to whoever was holding it? Nope, only the energy moved. The coils moved back and forth. They oscillated. But the energy flowed from one end to the other. Okay, so that's a primary wave, a P wave. After, at our seismogram station, after the P wave arrives, what then will arrive?
Secondary wave.
And
S wave.
have you got all this stuff written down? Because I'm going to erase it if it's okay with you, because I'm just going to keep rewriting these in the same spot. Cody, have you got that?
Yep.
If you are a viewer on YouTube, after you have finished looking at my outfit and comparing it to previous outfits, please make sure you pause it so you can get this written down. I assume Eli's going to watch this. S wave. S stands for secondary. Why would they arrive second at the seismological station or seismogram? A little slower. And if a P wave was a transverse wave, how is an S wave going to move?
Up and down.
It's a longitudinal. I think I might have actually confused these. Hold on. Did I? Yeah, these are transverse waves. Please go back to P wave and erase it and write longitudinal. The information was right. I just gave it the wrong name. That was a longitudinal wave. The P wave where you wrote transverse should be longitudinal. I guess I was all out of sorts on that one. You'll have to forgive me. Do you understand the correction I'm trying to make here? The information was right. It does move in the same axis as the energy. It's just that I used the wrong vocab word. That's the P wave is a longitudinal wave. The S wave is transverse. And so in this case, the particles move, I'm going to use this symbol, to axis of energy motion. What does that symbol mean?
Upside down.
No, you have to know this from geometry. I know for a fact Mr. Snelly teaches this because when I was perpendicular. We usually indicate transverse waves, which is the right word, with this. And how I would have indicated this in real life was either a string or that same slinky. Other brands are available. Slinky's actually a toy. Coiled spring toy. Held on one end and moved up and down or side to side. There are two different 90-degree variations. And so, let me see, I could probably do it with this string, which is actually a lanyard. I could hook it into here. There's no way this is ever going to show up on screen, but especially not if I do it like that. Excuse me. Yeah, this is going pretty good, actually. She came out. But you know what I mean. Like if it's moved in the axis, the particle mode, the actual matter, the particles move either up and down or in and out, but either way at 90 degrees to the motion of energy flow. Okay. As another little clarification, I don't know exactly how to indicate this, but which of these can travel through a liquid? There is one of them can move through a liquid, the other one can't. Do you remember which one's which? Primary waves can move through a liquid, so please write that down. Move through liquid. And that's pretty important because that's how we map Earth's interior. That's how we know, that is, remember, we don't really prove or know things in science. That's the evidence we have that much of Earth's interior is liquid, is because primary waves can travel through a liquid and secondary waves cannot move through liquid. And so a seismogram station at a certain distance away from this one where there's a liquid in between them, presumably the mantle, the P waves will make it, but the S waves won't. And that's one of the ways that we know that Earth's interior is largely liquid. And then finally, do you have the S wave stuff written down?
Yeah.
And then finally, surface waves, which is a kind of a combo, but they're also, well, we'll just write it down. Surface waves. Yep, slowest. And they move in kind of a circular motion. And when I say they, the surface itself is moving in kind of a roiling sea-like, the swell of the ocean motion on surface. And I'm not going to write this down, but can you guess which of these causes the most damage historically and usually to human surface waves? Yeah. If you can imagine buildings that are, built by human beings, because that's who does this, being caused to roll as if they are on the ocean, that's not usually good for the building. Now, how do we get around that? That's the next part of the lesson, really, is how do we measure the amount of an earthquake, the magnitude of an earthquake, and how do we prevent damage from earthquakes? And does this apply everywhere? Well, let's talk about it. So step one, let's not do blue. Let's do a different color. I guess black. Earthquake magnitude. What's happening in planet Earth when there is an earthquake? Let me start by asking this question. What provides the energy for an earthquake? Let me back it up one more. Do all celestial bodies, do all the planets in the solar system experience earthquakes? Well, obviously not, because they're not all called Earth, but do they all experience planetary quakes? That's a yes or no question. No. Why not?
Because some are gas.
Okay, that's true enough. Yeah, some don't have a solid surface at all, so that discounts 4 of them, probably. Of the remaining 4, do you think that Mars experiences, we would say probably Mars quakes? No. Do you think Mercury experiences Mercury quakes? No. Do you think Venus experiences Venus quakes? Yes. Why? So what's the difference? I'll just draw a little diagram here, and I'm doing this as a kind of an exploration of the planets, which you should probably know. This one's Earth. That's too big for Uranus. Uranus was too big, so I need to erase and start over. Okay. Mercury? Not really. Venus? Of earthquakes, yes or no? Ding, ding, ding. This one does, though. I don't know what I said at this point. Earth?
Yes.
Yeah. Well, I said none of them do because they're not Earth, but this one experiences crustal quakes. Mars? No, not anymore.
I didn't really.
Jupiter?
No. I didn't realize Mars was
Saturn?
small. No.
Yeah, it is pretty small. Uranus? Neptune? No. Why? Those last 4. Also
Neptune is too small.
good. Yeah, these are gas giants, so they do experience surface phenomena, but not really. We would probably just call it storms. Maybe they're allegorically similar, but we would just call them storms. Okay, but what's going on with Mars and Mercury? So we have these, what are called the terrestrial planets, which means that they're made of rock. Why don't they all? What is the driving force that only, it seems like, Venus and Earth have?
They're about the same size.
Okay, that has to do with it, but it's not the whole answer. I will give you a hint. Evidence suggests that Mars and Mercury and Earth's moon in the past did experience quakes, but don't really anymore. Yes, that's true. But even after it was part of Earth, after it had become divorced from Earth, but before today, evidence suggests it did experience moonquakes. So what's going on? Why would these small ones not?
Because they don't have enough mass.
Okay. They have never at any time had enough mass. And the part that you're right about saying anymore is that they are, well, first of all, I'm going to label as terrestrial planets. The smaller ones, there is a direct correlation. The smaller ones do not experience any kind of tectonic activity because they have cooled down to a point where their mantle is cold. You know, like when things cool down, you have tea. Yeah, this isn't a great example because your tea is cold already. I made it cold tea on purpose. But imagine if you had hot tea. I think you could probably imagine that. As time goes on, it cools down. The laws of thermodynamics apply. Everything cools down. You'll remember from chemistry too. Everything, heat is always the transfer of energy from a warmer object to a cooler one. Over time, these bodies cool down and their tectonic activity ceases because that is the energy that drives tectonic activity. So let's write that down. The energy driving tectonic activity. Do you know what I mean by tectonic activity? Give me some examples. Give me two examples because there are basically two examples. Oh, okay, sure. Convergent and divergent plate boundaries. Sure. What else? I was thinking of two different examples, but what are the symptoms of tectonic activity?
Oh,
like how do what is it? Yeah, we call that probably an earthquake, but and what's the other one? Okay, yeah, volcanoes probably. Like those are the ones that human beings would notice on our scale. You know, like so mountain building, yes, but that happens usually over many generations of human beings. And the continental drift, of course, but that happens over even longer periods of time. So the ones that humans would notice as tectonic activity are earthquakes and volcanoes. And the energy that drives this is, in one word, okay, specifically convection. So these bodies, Mars, Mercury, and the Moon, even though there's evidence that they did have these activities, tectonic activity in the past, don't anymore because they've cooled down enough that convection is no longer driving them. This is how convection works. If this is a section of Earth, I'll show you, this is the crust. This is where your house and your mom's house are. This is the crust. This is a very, very not to scale drawing. What's down here? If this is a section of Earth, what's down here? What's even downer? Core. All this stuff is asthenosphere. Were you briefed on the difference between asthenosphere and lithosphere? Okay. In earth science, a lot of times, depending on the context, we really don't use the words mantle and crust so much. We use asthenosphere and lithosphere. Asthenosphere meaning the kind of plasticky fluid layer of Earth, and lithosphere meaning the more or less rock-like. I'll write those down. Plastic fluid. Plastic meaning not made of the material plastic. I should point that out because some people are confused about this. Right? This is a kind of what we call plastic. The material is plastic, right? But that word actually means in material science, even though this is a material, in material science, plastic means that it's moldable. And it usually means something like, kind of like, if you think of silly putty or Play-Doh, good catch. Not so much that it flows like water, but that if pressure's put on it, it can move. It can change its own shape. That's what plastic means. But it also does flow sometimes, depending on its temperature, and so it's also fluid. Whereas the lithosphere, oh, by the way, asthenos is Greek for weak. Like in the way that a human being could be weak. Who's a weak person? Let's not go through examples. A cat. A cat. So asthenos is the Greek word for weak. And that means, and it's not that this is in today's culture, that kind of has a negative connotation. Obviously, or to me, it seems like it should be obvious that the asthenosphere, like we're not throwing shade at the asthenosphere because it's weak. It's just the way it is. It's not hard and rigid like the lithosphere is. This word lithos means stone. So the asthenosphere is able to flow and move in a way that the lithosphere is not. And because it's hot down here, I forgot to ask you that question, but by the way, the core is hot. Little thing about the core, it's hot. When the material in the asthenosphere gets hot because it's near the core, it lowers in density and rises to the surface, where it does what? Cools, increases density, and then sinks back down. This is a convection current. This is what drives plate tectonics, and the fact that our celestial body that we love so much, planet Earth, still has residual heat from its formation and has heat from ongoing nuclear reactions, drives this convection, both for volcanism and earthquakes. So that's what, sorry, go on.
And it would be called a hot spot when it's on.
Sometimes, yeah. There are multiple of these happening in the asthenosphere all over, and of course the asthenosphere, like planet Earth itself, is three-dimensional, not flat, although some people want to argue about that. But since the asthenosphere is three-dimensional, there are minor and major variations of this happening all over, and sometimes a very localized one would be a hotspot. Yes, absolutely. So the convection is what drives the entire process of tectonics, and that is what causes earthquakes. Now, what would make an earthquake strong or weak? Well, for that, do you have your book? So if you could turn with me to this diagram on page 529, which I really like. This is a stress-strain curve. Every material has a stress-strain curve. Is this showing up on the screen? I want that little diagram in the corner. Can you just see real quick? This one here?
No, it's too low.
Oh, too low. Like that?
Just a little bit too high.
That?
Perfect, I think.
Okay. As long as that graph showed up at some point, someone can pause it if they want to look at it. So every material has this stress-strain curve. You can see it on there. We have elastic deformation, which is related to this word plastic, which means that it will bend but will return its shape. So I'll give you an example. I mean, every material has this. I could literally use any example, but the easiest ones would be, so this is, you can see these individual fiber optic bands. If I bend them, they kind of spring back to shape. That's elastic deformation. There's a point at elastic deformation, which is called plastic deformation, which plastic meaning, again, like that silly putty or clay, where if I put a force on it, I put stress on it, it will retain that shape. Not spring back like elastic, but it will retain the shape of plastic. The relationship between elastic deformation and plastic deformation is different for each object, but you can imagine, I'm trying to think of one that would have a pretty shallow stress-strain curve so I could show you both plastic and elastic deformation. If I had thought about this even a little bit ahead of time, I'm sure I could think of something. I'm really tempted to use already chewed gum, ABC gum, but that's not probably a really good idea. Yeah, let's use paper. That's great. I have here the currency that some of these people know as ramrods. So if I put a little bit of stress on it, look, it's elastic. Is this showing up at all? Probably. I mean, it's paper. If you can't see this demonstration, get your own paper and try it for yourself. But if I put enough force on it, there we go. Now it's plastic deformation. It'll stay this way. Does that kind of make sense? So elastic, it'll return to its original shape. Plastic, it will stay in that shape. And then at some point, there's a failure. If I put enough force on it, the material fails. And that's the point at which in Earth materials, that's where there's an earthquake. So up here. So the reason an earthquake happens as a more or less discrete individual event, which is what an earthquake is because of that. So there's force on these two blocks, and at some point, it builds up force elastically, and at some point that energy is released, and now there's an earthquake all of a sudden, instead of happening continuously. And so that failure is when there's an earthquake. So that's why earthquakes, and then depending on the amount of force on those, we get different magnitudes of earthquake, which include, we can measure those by the Richter scale is the most common one, at least on the news. and the Mercalli index. These are the two that appear on your test. You can look at those on your own time, and they're on your chapter review. There was another thing I was going to say, the earthquake magnitude, and then, the effects of an earthquake on human structures have less than 30 seconds. You will look up the Mercalli index, which relates to human structures, and the Richter scale is a mathematical index of how much energy is expended in an earthquake. Do you have questions? Why did you take so long is a good question. Mercalli index, Mercally. I.